Welcome back, Quadrature fans. My name is Marion and today we'll continue our geometry for quadrature. And it's a subject that I'm actually learning. There's a lot of ignorance on my part. Hey, but it's okay. I'm having fun with it, and I welcome your feedback. I really need it desperately. Okay, affine geometry from Wikipedia. The definition, zoom in on this. It says, in mathematics, affine geometry is what remains of Euclidean geometry when not using the metric notions of distance and angle. That's pretty interesting. Not using metric notions of distance. We don't have this. Or angle measurement. This. Don't have it in affine. We have it in Euclidean geometry, but we don't have it in affine. So what are the consequences of not having this? I'm trying to sort that out. I might need your help there. So, okay, we don't have a ruler, we don't have a protractor. We're kind of in a pickle, huh? Okay, well, let's, the problem is that, okay, that's the definition according to Wikipedia. And I'm trying to relate this to, Cavalieri's principle. And you've seen Cavalieri's principle. There's a deck of cards, and you can shift it, right? And the area doesn't change. But I don't know. I've done a search, at least Google search, on affine geometry and Cavalieri's principle. I'm not getting too many hits on it, so I don't know. I'm not a mathematician, so I wouldn't know. But to me, it's kind of a no-brainer that this Cavalieri shift is affine. I don't know. Maybe I'm wrong. Maybe we need to give it a code name until I get your feedback. Well, what should we call it? You got a good code name for this? We can't call it affine because maybe it isn't affine. I don't know. How about COVID? COVID affine. All right. Affine. COVID affine geometry for now. That's our code name until we get this resolved. We're going to have to call it COVID. Because it's a little bit crazy, and that's what happens when you're in a lockdown. See, blame it on the COVID, right? That's okay. Remember, in 1665, Newton, there was the Great Plague of London. What was it, the bubonic plague or something like that? And they were in a lockdown. Where was he? Was he in Cambridge? I don't know, one of these fancy universities in England. And they sent him home. They said, Newton, go home. So he went home, and he had time on his hand, and he doodled, and well, guess what? He doodled up calculus. So, maybe this is similar. I don't know. That's what happens in lockdowns. You start thinking crazy thoughts. Okay, all right, enough of that. COVID affine, yes. I'm having fun, that's what counts. I don't get paid for doing math. I just do it, dabble. That's all right. So here's our situation with Euclidean geometry, and we have a right angle. And remember, in Euclidean geometry, there actually is such a thing as a right angle. See, we can actually, we can nail it, right? We can measure it. Euclid knows about it. So we got a right angle. Here we have a situation, a basic rectangle. Here's B, here's A. Those are the dimensions. So, well, let's see, what do we have? From an Euclidean perspective, well, you can see the area, that's B times A, right? The height times the base. B times A, that's called area. And the slope, according to Euclid, is rise over run, or B divided by A. That's the diagonal slope. And, of course, it's always good to even ask questions, what is area and what is slope? And you might think, well, that's a trivial question. By high school, you ought to know what slope is and what area is. But it turns out that it's like asking a physicist, what is energy? I mean, it's a profound thing. It can be. It seems to be this relationship of B times A in an algebraic setting, that's area. And B divided by A, that's slope. Now, when you think of slope, you might look at this diagonal slope and you say, well, it has a length, and it has some angle, but I don't know, that's not the right way to think about slope. Nothing's mentioned about this distance, which requires, what, Pythagorean theorem? Well, no, we don't need to. Even though we are Euclidean, we don't need Pythagorean theorem, right? It's a relationship of B divided by A. So don't think of it as a literal segment and an angle. Think of it as B divided by A. That's our slope of this diagonal. And well, let's compare that to affine. Well, let's just agree. The affine gets calibrated, and because affine, at least that's the way I understand it, he can't tell scenarios of this to this. So okay, he just grabbed whatever Euclid says. Your B, your A, and your slope is B over A, and your area is B times it. So in this scenario, Euclid and affine agree. Okay, we're calibrated. No problem. Now we're going to do a shift. A shift of, some kind of a shift here. So we're going to take this and shift it like this. And I'm not specifying how much I even shifted it. So, I mean, this could be a little bit, this could be a lot, this could be astronomical. That's not specified, okay? So, how much I shifted. It's just shifted. And so we ask, what is our area? What is our slope? And to Euclid, he looks at this and he would say the area of this thing, well, first of all, it's unchanged, but it's the base, it's the B, the height, which hasn't changed. Because, my card hasn't changed, but this distance hasn't changed, right? This is still the same. B is B. Euclid would have no problem with this. He measures this, he measures it, he says, good, you're good to go. B is B. But what about the, Euclid would say, okay, it's base times the width. See this thickness right here? The distance between these parallel lines, according to Euclid, that's W, right? And it happens that W is equal to A, right? You can see it. We're maintaining parallelism. See it? So W, yes, it is equal to A, but that's what Euclid says, that you're B times W. And that's the area according to Euclid. Now the question is, what is this diagonal slope according to Euclid? Well, we don't know because I didn't specify how much I shifted. It could be a little, it could be a lot. And so we don't know. We have to say question mark. I didn't tell you how much I shifted it. So what is that? We don't know in the Euclidean system. Well, let's look at it from affine perspective. To affine, he looks at this thing and he says, well, area, it's just B times A. The thing with affine is he has no notion of the distance from here to here. There's this W that Euclid sees. To affine, that is a total nonsense. He doesn't have Pythagorean's theorem. He doesn't have a protractor, a ruler, nothing. It's total nonsense. W to him, the distance from here to here. That's nonsense. You can't say area is B times W. W doesn't exist. He doesn't know what it is. It's just irrelevant. All he has is A. Now, the problem is, in affine, you kind of have to put quotes around the term A. Because obviously, as we shift it, to Euclid, you measure this thing, and then you come down to here, and it's obviously stretched. Right? You can see that it's, A is not the same. It's been dilated, stretched. But affine doesn't know that he's been stretched. To him, this distance, A, you could almost call it Chaka. You know who Chaka is? Yeah, it's Euclidean graffiti. And Euclid put A on him, and that's how he terms it. He says, well, I'm still, I'm still here. I'm still an A. I haven't changed. I'm A. Here's 0, A over 2, A. So, let's think about it. We know that under Cavalieri shift, Cavalieri's principle tells us that the area remains the same, invariant under a Cavalieri shift, right? So this one's invariant, A, right? And B, well, B hasn't changed. Euclid certified it. Euclid can actually measure that and tell me, yep, your card is the same. It hasn't stretched, right? The thing that has stretched is this. But, affine, So, this is invariant. Invariant. You've got A, area, and you got B. Now think about this. You really got to think this through. If A is invariant, constant, under a change, and B is invariant, what does that make to B. It has to be constant. It can't change. It's invariant. This one, A, is invariant. And that's kind of the rub, because Euclid looks at that and he says, yeah, but you're not A. You've been stretched. You're A dilated. So there's a little bit of a conflict there. How do we resolve this? You know, this is, and I'm struggling with it too. You know, area is invariant. This distance, B, no problem there. That's invariant. No change. Therefore, A, it has to be invariant, no change. Under a Cavalieri shift, distance, and we use the term distance in quotes, because we don't have much of a notion of metric motion. So he's invariant. He doesn't know that he's shifted. He can't tell. He's just Euclidean graffiti. It's Chaka. That's all it is. This is Chaka over 2. And the same goes with the B. It's all graffiti to him. But, you know, he takes it and, okay, that's what it is. And so what is slope? Well, slope, according to affine, and remember, we're talking this COVID affine, equals B divided by A. And look, we said that B is invariant, didn't change. And we also said that A is also invariant. So what does that make the slope equal to? It didn't change. It's invariant. It's B over A. It's the same as it was here. The slope. And this is something that kind of hit me, and maybe, well, this is where I need the feedback, you know. I mean, under a Cavalieri shift, I'm saying that not only is the area invariant, but the slope contribution is also invariant. And one way to look at it is kind of a satellite view from the top. Okay? Look at it, a bird's eye view. You're looking at it from a satellite, okay? And here you see a situation where, you know, you see 0, A over 2A. That's your run. Okay? And from a satellite perspective, you look at this situation and you see the same thing. You see 0, A over 2A. Can you tell the difference? If you look down, you know, here's our shifted thing, and I'm looking down, and to me it's, oh yeah, the run is 0, A over 2A. So it kind of agrees with the Euclidean system, and so, okay, cool. So here we have our geometry, and of course, we need a little bit different geometry if you x squared plus x. So I've done that in my previous video. Well, the plot of that, well, that's kind of like this, from 0 to 1 or something. So here is and here's this one. And if we just do a straight shift, a linear shift, shift this thing down, then we're going to get kind of like this. And so the total, so what we get is these two areas here, like that, okay? X squared plus x. And problem happens right here where you get this void. So linear shift, that's not good enough for us. We need something a little bit better. We need curved geometry, which looks like, well, something like this. We can do it. We maintain our parallelism, right? Like this. But we go something like this. Oh, what's the matter with my pen? Oh boy. And so, in this system, well, our diagonal looks like this. So here's A over 2, A, 0, 0, B over 2, B, right? And if you plot it in here, it looks like this. It's curved. Notice our diagonal, which before, to a Euclidean perspective, looked like straight as an arrow. To us it looks crooked. But that's what's needed in order to make this thing fill properly. You see this? We want a geometry that adds nicely so that in the end we get this kind of a, we get this. Let's see now. I'm trying to draw it. And something like this. Anyways, these two areas are the same according to Cavalieri principle, right? No matter how you shift it, even a curved shift like this doesn't change area because the number of cards, the thickness is the same, number of cards is the same, area is the same. But, you know, the slope contribution of each individual function, it doesn't change no matter how you arrange it. Eventually end up like this. And with this curved affine, we can actually stack it all the way down. And now they add good, and this is what the final result, if you plot this on a plotting calculator or a computer or manually, this is the final result that you get. It's this curved thing, right? That's what we want. We don't want this thing. But in all of these things, no matter how you shift it, the slope contribution is the same for the system. And then finally, well, our crazy geometry, and I got a really nice stack of cards for this. Take a look. These are business cards, right? Oh, this is nice. Look at that. Ooh. Something like that. Woohoo! So we can do, well, let's do some crazy shifts, okay? Let's say we start out, let's see. Let's say we start out like this. We start here, right? And then we're going to do a kind of something like that, right? We're going to literally take this thing and shift it like this. Imagine I'm doing it. That's kind of ugly looking, but I'm trying to do it. Can you see that? Does it show up? It's on a white background.
Yeah.
Yeah. So anyway, so I'm shifting it. I have not changed area, right? That's area doesn't change in a Cavalieri shift. And okay. So now we have our situation. What does it look like? So like this. This is what the diagonal looks like here. 0, A, 0, B, right? And you can see that A hasn't changed. We rotated it. Well, there's perfect agreement that A is the same with this thing, okay? Fine. But obviously B has been kind of stretched. We've definitely done this. But of course, I'm claiming that this COVID affine doesn't know what's happening to him. He thinks he's just like this. To him, B is invariant. Okay. Now, let's do a rotation the other way. What happens if you take this, okay, and now you do some kind of a shift like this, right? Can you do that? Perfectly fine, right? I can take this shape and take another step and draw it on my stack of cards and do another transformation. And that's going to be wild and crazy, right? So we got, whoa, it's going to be a little bit shifted like this. So, right? That's what we have. And then from here to here. Right? And so it's even more crazy, right? I don't know, something like that. 0, A over 2A, 0, B over 2B, right? Something like that. This I call Salvador Dali type geometry. All right. Because, wow, this is wild and crazy. And the thing about this one is that here, this bird's eye view, it's kind of, doesn't work very well, right? Because no matter which way you look at it, you kind of see things wiggle. But what have we proved before? That we proved that A, and B are invariant. Okay, we did that before. Well, proved it using a willy-nilly proof, but we concluded, at least I concluded, that A is invariant under Cavalieri shift, right? Or B is invariant, distance. So if A and B are invariant, well, what's the area? Area is equals B times A. Same as here. What's the slope? M equals B divided by A. Same thing. Just as if it was in a right angle state, no difference. It's the same thing. No matter what you do then, in a Cavalieri shift, he's invariant. So, there you have it. Crazy math, crazy geometry, COVID affine. I welcome your feedback. Anyways, as Professor Theoremus Antiquatus would say, before there was calculus,
There was COVID.
there was COVID affine.